Hello everyone. Thanks to everyone for watching this video. My name is Qi Dang. I am an architect and engineer. Today's video is titled Column buckling, and it is going to provide you a broad overview of column buckling and also the analysis of elastic compression members. I am going to give you an overview of what I am covering in today's video. First of all, we will have a look at some fundamentals of the elastic behavior of a compression member, then move on to calculate the deflection of the typical column, then wrap up with conclusions. The compression member is a type of axially loaded structural element. Another type is the tension member. Very stocky compression members behave in the same way as do tension members, until after the material begins to flow plastically at the squash load My equal to A times Fy, where A is the cross-section area of the members, and Fy is the material yield strength. However, the resistance of a compression member decreases as its length increases, in contrast to the axially loaded tension member, whose resistance is independent of its length. Thus, the compressive resistance of a very slender member may be much less than its tensile resistance, as shown in this figure. This decrease in resistance is caused by the action of the applied compressive load N, which causes bending in a member with initial curvature, like this figure. In a tension member, the corresponding action decreases the initial curvature, and so this effect is usually ignored. However, the curvature and the lateral deflection of a compression member increase with the load, like this figure. The compressive stresses on the concave side of the member also increase until the member fails due to excessive yielding. This bending action is accentuated by the slenderness of the member, and so the resistance of a compression member decreases as its length increases. The elastic buckling load NCR provides a measure of the slenderness of a compression member, while the squash load Ny gives an indication of its resistance to yielding. In this video, the influences of the elastic buckling load and the squash load on the behavior of concentrically loaded compression members will be discussed. Next, we will introduce the buckling of straight members. A perfectly straight member of a linear elastic material is shown in Figure A. The member has a frictionless hinge at each end, its lower end being fixed in position, while its upper end is free to move vertically but is prevented from deflecting horizontally. It is assumed that the deflections of the member remain small. The unloaded position of the member is shown in Figure A. A concentric axial load N is applied to the upper end of the member, which remains straight, as shown in Figure B. The member is then deflected laterally by a small amount V, as shown in Figure C, and is held in this position. The elastic buckling load NCR of the compression member can be determined by finding a deflected position, which is one of equilibrium. The differential equilibrium equation of bending of the member is this equation, where EI is the flexural rigidity of the compression member. This equation states that for equilibrium, the internal moment of resistance must exactly balance the external disturbing moment at any point along the length of the member. When this equation is satisfied at all points, the displaced position is one of equilibrium. The solution of this equation, which satisfies the boundary condition at the lower end that VO equal to 0, is this equation, where delta is an undetermined constant. The boundary condition at the upper end that VL equal to 0 is satisfied when either delta and V equal to 0, or KCI equal to 1 over N, in which N is an integer. so that we have NCR and V equations. The first solution defines the straight stable equilibrium position, which is valid for all loads n less than the lowest value of NCR. The second solution defines the buckling loads NCR at which displaced the equilibrium positions can exist. This solution doesn't determine the magnitude delta of the central deflection. The lowest buckling load is the most important, and this occurs when n equal to 1, so that we obtain the NCR and the V equations. The elastic buckling load NCR and the elastic buckling stress sigma CR equal to NCR over A can be expressed in terms of the geometrical slenderness ratio L over I by this equation, where I equal to the root of capital I over A is the radius of gyration. The buckling load varies inversely as the square of the slenderness ratio L over I, as shown in this figure, in which the dimensionless buckling load NCR over NY is plotted against the generalized slenderness ratio, where NY equal to A times Fy is the squash load. If the material ceases to be linear elastic at the yield stress Fy, then the above analysis is only valid for lambda bar equal to the root of Ny over NCR and greater or equal to 1. Now we move to the bending of the compression member. The bending of the compression member with initial curvature, shown in this figure, can be analyzed by considering the differential equilibrium equation, which is obtained from the previous equation for a straight member by adding the additional bending moment minus n times VO induced by the initial curvature. If the initial curvature of the member is such that VO equation, then the solution of the new differential equilibrium equation, which satisfies the boundary conditions VOL equal to 0, is the deflected shape of V equation, where delta over delta O equal to this equation. The maximum moment in the compression member is n times delta plus delta O, and so the maximum bending stress is n times delta plus delta O over WEL, where WEL is the elastic section modulus. Thus, the maximum total stress is this equation. If the elastic limit is taken as the yield stress Fy, then the limiting axial load NL for which the above elastic analysis is valid is given by this equation. By writing WEL equal to 2I over B, in which B is the member width, this equation becomes a new equation, which can be solved for the dimensionless limiting load NL over NY as this equation. Alternatively, this equation can be rearranged to give the dimensionless limiting load NL over NY as this equation, where the expressions of phi and lambda bar are shown here. The variation of the dimensionless limiting axial load NL over NY with the generalized slenderness ratio lambda bar is shown in here. For the case when eta equal to the quarter of NY over NCR. For stocky members, the limiting load NL approaches the squash load NY, while for slender members, the limiting load approaches the elastic buckling load NCR. From conclusions, what we learned? For the hypothetical limiting case of a perfectly straight elastic member, there is no bending until the applied load reaches the elastic buckling value. At this load, the compression member begins to deflect laterally, and these deflections grow until failure occurs at the beginning of compressive yielding. This action of suddenly deflecting laterally is called flexural buckling. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative, and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.